In section 1 of chapter 3, we're going to be going into factoring, but before we do that, we're going to be using the area model for polynomial multiplication. Alright, imagine we had a rectangle, and it measured 5 units tall, 9 units wide, and I asked for you to find the area. Now, some of you would be able to just tell me what the area is because you've just memorized how to find area of rectangles. It's length times width. That's fine. But I really want you to understand why that is. The reason behind how we find area is when I say something's 5 units tall, that means you could separate it 2, 3, 4 into 5 bars. And each of those bars is 9 units long. You could also do the same with the with the width. 1, 2, 3, 4, 5, 6, 7, 8. And then what you could do is you could then count all of those little boxes. And this is what we did back in elementary school. And then you learned about multiplication. Multiplication is just repeated addition. When I say 5 times 3, what I'm saying is I have 5 groups of 3 being added together. But we just memorized that multiplication fact, because we do multiplication so much you just now have internalized 5 times 3 is 15. But multiplication is just repeated adding. When I'm saying 5 times 9, what it means is I have 9 groups of 5. And all you're doing is going 5 plus 5 plus 5 plus 5, and you're doing that 9 times. But now we're at the point where you can just say, oh yeah, I know what 5 times 9 is. 45, and that's my answer. But I really want us to get across what we're actually doing when we're finding area. Because that's going to allow us to extend that concept into an algebra 2 domain. So if I have 5 times the quantity 3 plus 1, what you could do is you could say, oh, well, I have a rectangle that is 5 units tall, and then its width is 3 units plus an additional 1 unit. And you could do this 2 ways. You can either add the 3 and the 1 together and then multiply it by 5, or you could see this as finding the area of 2 separate things. 5 times 3, which is 15. 5 times 1 is 5, and then you could add them together. That's where the distributive property came from, where you distributed the 5 across both terms. Or you could have just taken the 3 and the 1 and gotten 4, and then multiplied the 5 times the 4. Either way, the answer is 20. So realize there are 2 different approaches to finding the area of that box. What happens when there's a variable thrown in? It's the same thing. I have a height of 5. I now have a width that I don't know, which is x, and a width that I do know, which is 1. Now in this problem, I don't have 2 options to pick from. In the first problem, I could either distribute the 5 or add the 3 and the 1 and then multiply by 5. You could do either or. In this problem, we can't do either or because I can't combine these, meaning the sum, making it equal to 4, I can't do that here. So I'm only left with the distributive property. I'm only left with distributing the 5 times x and the 5 times 1. And the reason that works is because that area model, you could split in half. Actually, I should do this in red. And now I have 2 rectangles. One rectangle is 5 units tall and x units wide. So if you multiply those together, you get 5x. And the other one is 5 units tall and 1 unit wide. When you multiply those, you get 5. If you wanted the area of the entire rectangle, you would just add the individual rectangles together. And that is what happens when you distribute the 5. So this is just a visual representation of the distributive property you've been doing since grade school. Again, we're going to expand upon this further. Now what happens if you have a binomial times a binomial where each one has a variable? Well, that means I'm going to have an even bigger rectangle where one side of it is going to be measured x plus 2, and the other side is going to be x, and then we have to kind of conceptualize the idea of a -7 as a length. That's a horrible little box. If I want to find the product of x plus 2 times x minus 7, that's the same thing as finding the area of that box I just made. Seeing as how that box has measurements of x, I can't multiply x minus 7 and x plus 2 directly with one another, so we break these into smaller regions. If I find the area of all 4 of those boxes and add them together, that will be the area of the entire original box. All right, so I'm going to find the area of the 4 boxes. This box right here is going to be x tall, x wide. So I just multiply the length and the width. X times x is x to the second power. It's x squared. If I want to find the area of this box, it's x units tall, -7 units wide. X times -7 is -7x. Bottom left box is 2 units tall, and then x units wide, so that'll be 2x. And then lastly but not least, this is 2 units tall and -7 units wide. 2 times -7 is -14. Add those together, you'll get x squared minus 7x plus 2x minus 14. The two terms in the middle are like terms. They both have an x, so I can combine those together to get -5x. And now I have discovered the area of this shape. Now I know some of you in your head are probably thinking, Mr. Silva, wouldn't it have been faster? I could have skipped the whole area model if I just did x times x is x squared. X times -7 is -7x. 2 times x is 2x. And then 2 times -7 is equal to -14, or as you guys know it as FOIL. Yes, that is faster. The problem with foiling is it's an algorithm. It's something to shortcut through the area model, which is fine when you're first learning it. But what we're going to be doing in this chapter really relies on us understanding the area model and how to utilize it. So I'm going to request that on every single one of these problems, I know you could do it faster by doing FOIL. I don't want you to FOIL. I want you to specifically use that area model because it's going to help us later on in this chapter. Here's the last one that I want to talk about, because this is one that you really can't FOIL super easily unless you manipulate it, which is the quantity x minus 3 quantity squared. Realize that as a problem is the same thing as the following. It is just x minus 3 times itself. And now I'm going to reveal to you why when we say to the second power, when we say it's squared, we didn't mean that nonchalantly. We didn't just say like, oh yeah, it's second power or squared. Because if you construct the area model for this, it would be x, and then a -3, and then this would be an x, and a -3. This would be my area. Notice that the height and the width are the same length. When the height and the width of a rectangle are the same, it's called a square. That's why second powers are called squares, because if you do an area model to identify them or represent them, they will always make a square. This will be incredibly important once we start doing a technique called completing the square. It is based on that idea. Completing the square is also one of the concepts that most Algebra 2 students struggle with immensely. All right, so let's find the area of this. X times x is x squared. Negative 3 times x is negative 3x. Negative 3 times x is negative 3x. And then negative 3 times negative 3 is positive 9. Here's something you might latch onto when doing the area model. It's not always going to happen, but if there are like terms, they typically show up in diagonals, meaning you can skip one of the steps. It's going to be x squared. The negative 3x and the negative 3x are like terms, giving you negative 6x. And then there's a plus 9 at the very end. Here is our multiplied out binomial square.